Let's take a look real quick, and then I'll shift this over.
Where am I? 93, okay. 48. Oh, yeah. Prove the identities, okay. So just to remind you guys, I didn't bring hard copies. I'll bring hard copies tomorrow, but you can print this out for yourselves. The trig identities are up in Canvas. I'll bring some hard copies tomorrow of this, and remember how this works. Everything above the black line, you need to know. You need to memorize, or you need to have a way to remember them somehow, right? So I kind of don't memorize all of these. I build them when I need them. Or you just straight up memorize all of this, right? I would hate to have to memorize all of this. I'd rather think of ways to kind of get them when I need them. Everything below the black line, still a perfectly valid identity. I'm not making you not memorize them because they suck or something. They're still great. And you're going to see them in the homework. But if I gave you a problem on the test or on something, I would give you the identity for these. You don't have to memorize these. So the one that I need for this problem, see here, tangent alpha plus beta, well, plus or minus, right? So if I look back at this problem, tangent a plus b, tangent a minus b, right? Do you see what I'm saying? Or you could even see what this is all about, right? One way or the other. That might even be better. I don't know. No. No? Yes? No? I don't know. So if I were you, I would start on this side. I would replace this with what it is. You could look it up. You don't have to memorize. You can just look it up. So when you're doing homework, you can use whatever the hell you want to, except solutions manual or the answer written somewhere, right? So totally look up the tangent a plus b formula. It's on the sheet I told you. Does this make sense? So I've replaced tangent a plus b with what it is, replace tangent a minus b with what it is, and then just start attacking it, start simplifying it as much as I can. Did you try to do that, or? I tried. Okay. So.
Say again. Could be, yeah. Because the first part of chapter 9 was about identities. We didn't know all, well, let's see, 9.1 through 9.3 is pretty much most of the identities. Yes, so. All right, so I'm going to leave that side alone because we're going to work with this side. Tangent a plus b. What is that? I can't zoom anymore. Okay. Tangent of a plus b. Remember how this works, plus or minus? So if I want plus, I'm going to choose all the top signs. You see how that works? If I want minus, I'm going to choose all the bottom signs. So that's why minus plus actually means something different from plus minus. We talked about that a little bit. So tangent of a plus b, it's going to be tangent a, top option is plus, tangent b. Now you see why I make my t's like this, so they don't look like pluses. And what is tangent a minus b? Oh, I'm sorry, I'm not done with this. On the bottom of this goes 1 minus tangent a, tangent b. And again, to prove this, I would take sine of a plus b, which we know that you're supposed to memorize that formula, divided by cosine of a plus b, and simplify it, and I would end up here. Not a big deal, right? We proved
the sine and the cosine, and then I can build secant, cosecant, tangent, I can build them all from just knowing what sine and cosine are, right? So that's where this comes from. It's just not out of nowhere. We could prove it. And then I want to divide by tangent of a minus b. Whenever I have something fractional divided by something fractional, how do you do a fraction divided by a fraction? Multiply by the reciprocal. So what I'm going to do, instead of making one big ass fraction with fractions in it, I'm going to multiply by the reciprocal of this. So what is tangent of a minus b? The top I'm going to put here. What would tangent of a minus b be? The top would be what? Sorry. Tan a minus here, right? Tan a minus tan b. I want the bottom option. You guys see how to read this? So if it's plus, I want the top option. If it's minus, I want the bottom option. Because in general, we go, what's the difference between plus minus and minus plus? Now you know. It's supposed to designate when you choose which one. So tangent A minus tangent B. Oops. And what goes on top? So reciprocating this. What do I choose here? 1 plus. Again, why? Because it's tangent A minus B, so I choose the bottom option. That's it. That's it. So there'll be 1 plus tangent A, tangent B. And now you just have to figure out what can I do from here. Oh, okay, sure. You could go ahead and multiply the top and the bottom. You can FOIL it out and hope that it's going to go somewhere. That could be the first thing you try. Or maybe it'll work, right? So that's not a bad option. We know we want this to end up looking like what? So whenever you're trying to prove an identity, keep in mind where you want to end up. So where do we want to end up here? We want to end up with a bunch of sines and cosines, right? Yeah. So it might be a good idea to rewrite everything here in terms of sine and cosine. So you might want to try to multiply first and then do in terms of sine and cosine, because if you do it right now, it's going to be just sines and cosines running crazy all over the place. Do you at least see how to start this problem? Who asked that question? I'm sorry. Do you see how to start it now? Okay. So I don't want to do too much of this for you, but if you don't know the first step, you're dead. Yes.
I just want to know what tan B times tan A tan B looks like.
Where are we looking? Sorry.
When you do FOIL at the end.
Yeah. So like here, and you're talking about right here.
That or same thing tan B.
Yeah. So it'd just be tangent squared A.
Okay.
Times tangent B, right?
Okay, and then the other would be tangent A tangent B squared.
Yes. So when you do this one times this one, yeah, exactly. Yeah. It's just like x times xy is x squared y, right? Yeah. So when I multiply like terms, I end up increasing the power. I've got more and more and more of them. Yeah. So it doesn't matter what they look like. If they're the same thing, I can accumulate them with powers.
Is that the same thing as putting a 2 in front?
No, definitely not. When I add like terms, I can accumulate them by keeping track of coefficients, right? So, x plus x. Well, let's say tangent A plus tangent A equals 2 tangent A's. I'm keeping track of how many I'm adding. Tangent A times tangent A is tangent squared A. I'm keeping track of how many I'm multiplying. So that's really fundamentally all the coefficient is, keeping track of how many I'm adding. All the power is keeping track of how many I'm multiplying. So I don't have to write so much. That's really it. It's just shorthand. That's what a lot of math symbols are. It's just shorthand. Okay, maybe. Is that all right? I mean, is that enough to at least, you might not, right now, you might be looking at it like, how the hell does that work? Does everybody know how to try something here, right? either you go ahead and FOIL it out the way it is, and then you replace sine and cosine, or you replace sine and cosine now, and then try to start putting stuff together. I would think to maybe multiply them together first, so there's less stuff going crazy as you FOIL. Maybe, okay. You just gotta try it, and I really need you to understand, there is no blanket statement I can make. Like, every time you see an identity verification, you do this. No, I can't say that. I can't. You just have to try stuff. That's it. That's all it really is. And as you do this, I would print out that green sheet of paper from the Canvas shell and have it sitting next to me, or I'll bring some hard copies tomorrow. Just have that sucker sit next to me. So I'm like, see, I can try that. And if that doesn't work, okay, let me try that one, right? Yes?
How do you multiply 10A and 10B?
Sorry?
How do you multiply 10A and 10B?
How do I know to multiply?
How do you multiply?
Oh, you can't, all right? It's like saying, how do you multiply x and y? It's x times y. How do you multiply tan A and tan B? It's tan A times tan B. Yeah. Muhammad's like, well, that didn't help me. I'm sorry. I don't blame you. No? Okay. So, just FOIL this stuff out. There's tangents, who cares? FOILing works the same always, right? And then once I FOIL stuff out, I'm gonna replace everything with sine and cosine. Why? I don't always do that, but here I definitely want to, because I see the insert is supposed to have sines and cosines running all over the place. Maybe.
Why do we do this?
Say again?
Why do we do like proven trig identities?
Because they show up. A lot of what we do, math tries to model the real world. The real world is chaotic. So any situation we're in, it could be modeled by any function we've learned, and even some functions we haven't learned. So can there be a situation that it's modeled by trig functions, but in order for me to kind of use it, I want to rewrite it? Yes. Has that ever happened in real life? Billions of times, right? So pre-calculus is really just learning how to walk with some of this stuff. If you go further in mathematics, you start to use this stuff to do real life stuff. Okay, so verifying trig identities feels like busy work, I know, but they show up everywhere, holy shit. If you go much further in mathematics, they just show up whenever they want to. Maybe. I will tell you, will this ever specifically show up anywhere? But the skill of working with these things is what we're developing. Yeah. Okay, I like it. So no, this won't help you buy car insurance, but it's not the purpose of everything. Anything else from homework, or just generally, or? All right, so if you feel like you're doing the homework and it says verify the identity, and you feel like, I wasn't told how to do this. You didn't tell me how to do this problem. No, I didn't. I told you how to do every problem. That's all I did. Each problem has its own thing. So I really want you to really hear me. You will do the wrong thing. You will. I do the wrong thing because I'll see something, I'm like, I think this will work. Oh, it didn't work. Not a big deal, who cares? Let me go back and try something else, right? Maybe? Yes?
So I have a question. So I know I can't be the only one who doesn't know like how to do any of this crap. I know we have to keep moving through our material, but like, why can't we spend a little more time on the fundamentals so we know how to add on to, you know what I'm saying?
So I need help then. Which, like in this specific problem, for example, does everybody, why did I choose this side to work with? Why did I choose this side?
Because the other side already has terms in, or has its terms in sine and cosine.
Yeah, but also there's something to do here, right? There's
you could try to find an identity. In fact, let's do this. I chose this side because the identity for tangent of the addition and sum of angles, the addition and difference of angles, is something we know. It's on the sheet. So it's a side that I can immediately do something to. So whenever I'm trying to verify a trig identity, and one side says sine of x, and the other side has all this shit, of course I'm gonna start with a side that has all the stuff, because then I can do stuff to it. I can't do much to sine, right? Some problems, both sides has stuff you could do to. So then you can pick either side you want to. So when you're doing identities, like I said before, you pick a side to start with and start to do stuff to it. You're trying to make it look like the other side. That's what identity verification is. How do you verify that something equals something? Well, you make this thing look like that thing. Then they're equal to each other, right? Okay, maybe? Okay.
Do you break it up?
Break what up?
Like when looking at these equations, do you wanna like pick the side where you can like break it up more? Or
Yeah,
where you
decide
can-
that you have things you can do to.
Rather than simplifying it?
Yeah, so I mean, if I, let's see. If I want to show that, if this is true, what do you got, Jeff? Yeah, let's do this. Okay. Which side do you think you'd start with if I wanted to verify that's true?
Oh, wait, no, no.
Which side would you start with if I wanted to show that this is true? All right, see, which side has more stuff that you can do to it? This has got more shit going on. It's a division. I can actually do the division. Do you guys see that? So this side has stuff I can do something to. I can't do anything to this side. Not really, and again, I'm trying to tell you the textbook standard method. And then once you get that, then I can start telling you about, okay, here's another. So for example, does everybody understand? This side has an actual math thing it wants me to do to it. Doesn't it want me to divide? So then I'm gonna try to do it, right? This side, it wants me to take a square. I can't do anything to this side. Please, dear God, if you think that this is x minus 4, stop, right? You can't take the square root of a difference of things. You can't do that. This side, I can actually try to divide these things, right? So for example, isn't x equal to the square root of x squared? Bless you. Then can't I divide that in there because you need like roots before you can divide, right? So okay. In some problems, it'll be really clear that one side has a lot of stuff you can do to it, and the other side is like sine of x or something. There's nothing you can do to it, right? Maybe? Okay. So then I would start with the side I can do stuff to. So here, tangent A equals B has an identity. I can replace it with that identity, and then I can start to do stuff to it, right? Okay. But let me show you something. Let me show you the first little modification to what I just said. What's the main difference between these two sides? What's different here? What's the main big giant difference?
Divided by x.
Yes. How do I make this divided by x also? If I divide this by x, I have to at the same time do what? You can do it. If I make the bottom times x, what do I have to do to the top? Yes. So the only valid way to divide something by x out of nowhere is to multiply by x at the same time. Didn't I just do nothing? Isn't that what we do every time? Like, how do you subtract these? How do you subtract those? Right? Don't say it's 3/6. Right? How do you subtract those? What do you have to do? You have to get
like denominators, right? So how do you get like denominators? Don't you multiply this by 3, and so you have to multiply the top by 3 also? So, the bare bones beginning thing you do is you identify which side seems to have more I can do to it. And it makes sense. If I have a side that I can do more to, I'll start doing that stuff to it and try to see if I can make it look like the other side. If one side says sine x, I've got nothing I can do, and the other side's got tangent x times cotangent x over the secant. Okay, I can start doing stuff to this side, correct? But kind of like the next level above that is understanding that I need, this side has an x under it. So how do I start to make them look the same? Well, I give this guy an x under it, right? Now what do I do from there? Well, why can't I multiply x by this stuff? What's the only way you can multiply something that has a square root on it by something else? The other thing also has to have a square root. So I can't do 3 times square root of 7, but I can do square root of 9 times square root of 7. Right? So what's x also known as? Square root of x squared. And what's x squared times x squared? And what's x squared times negative 16? So either you can start on the side that seems to have more you can do to it, or you start on the side that you can see, oh, it's missing this, so I'm going to give it this, right? That's kind of like what I do. Okay, so let me see. Okay, so that wasn't a trig thing, but it's the same idea about how to verify two things are equal to each other. So a lot of what I do goes off of the problems you guys have, and that's why I make room for homework questions. There are sections before this one that involve identity verification. Are there questions from the problems you had to do for those sections? And then we can talk about them, right? So if you're doing the homework and having issues, tell me which problems you had issues with, right? Let's see. So this is the one, 9.2, okay, so the very first section. So the very first section had very little in it. So the only things we knew from the first section of 9 were, let me see, here we go. Yeah, the Pythagorean identities and like the sign of negative x, the symmetries. That's basically all we knew. So with these are going to be much simpler because there's less options for what you can do. So again, if you had trouble with the problem, we could look at it. Or let's see, let's look at like number 29, for example. Okay. So in general, when you're in a class and you're having issues with problems, I don't know unless you ask me questions about those problems. And then I can do something about it, right? So we've discussed the basic idea of how to kind of verify identities. If it's not quite making enough sense, we could do some more examples. I don't know if there's an issue unless you bring it up. So let's try number 29 real quick. So this is a good example of either side you want to start with. It will be good. Does anyone see something you can start doing to one of the two sides? What's up? Oh. So our identities, the most basic identities. Can somebody give me the most basic identity for trig?
Sine squared plus cosine squared is 1. And the other ones are 1 plus tangent squared equals secant squared, and then 1 plus cotangent squared equals cosecant squared. Right? They all have trig functions that are being squared, correct? You guys, right? So when I have an identity that I have to verify, one thing I could do is to look for my squared stuff, if there is any. Because then I have an automatic identity I can use. So if sine squared plus cosine squared is 1, what's cosine squared, for example, then? 1 minus sine squared. And what's sine squared? 1 minus cosine squared. Anything I wrote useful on either side right now? Yeah, I see a sine squared right there. And notice also, on this side, there are only what's? Cosines. That's all there are. So do you see how there's multiple things telling you what to try first? And again, I'm not saying this is going to work, but these are what I look for. It's going to work most of the time. I see nothing but cosine, so it makes sense to rewrite this in terms of cosine. I see a squared trig, which is related to an identity immediately, right? So what do you get if you replace sine squared with what it is? So if I'm going to work with this side, what do I put here? Because that's what sine squared is, correct? So again, a huge part of this is understanding that when you're doing homework, you're completely allowed to look at notes, you're completely allowed to look at that sheet of identities, right? Eventually, you're going to have to get to the point where you don't need to, but when you're first doing this stuff, have that sitting next to you. So when you look at this, you're like, holy shit, I don't know. You say, oh, there's sine squared, that's involved in an identity, maybe that's going to help me. And you try it. And what's beautiful here? Right? What do you get when you distribute? Cosine x minus which is what that is, right? So I showed that equals that. Now, somebody else can take that same problem and start working on the other side. Can anyone see? Let's look at this problem again. Can anyone see something to do to this side? Can something happen to this side? What do both terms have in them? Cosine. So can't I GCF a cosine out? Right? So if I take a cosine x out, what's left? 1 minus cosine squared, right? I lose a cosine in each. And of course, 1 minus cosine squared is sine squared. So then, bam, done. I made one side look like the other side. So that's an example of either side would be good to start with. Okay. Is that all right? So far, so good? Okay. So that's what I mean by pick the side. Sometimes it's the side that actually has something you do. Sometimes it's the side that you kind of see what to try to do. So you just start trying something. And again, I don't know if you guys really understand what I'm saying. When you do these problems, if you pick the wrong thing, that is part of the process. Picking the wrong thing is fine, because that's part of what we do. How do we solve problems in real life? Is the first thing we think of, does it always work? If there's a problem, and you're like, let's try this, does it work? Does it always work? No. Does that mean you go, oh, well, shit, I guess we're going to have a water leak in the house forever, and everybody get used to it being like Venice in here. Everybody get their own little gondola. Yay. Get from the living room to your bedroom. What do you try? You try something else, right? I don't know. You guys understand what I'm saying? So
How many identities are there? Are there a few? There's a few. So obviously, some might not quite work to get you to what you want to have happen. So it's okay. So you just pick something else. So what could happen in these problems? Factoring can happen. So how do I know I can factor? Because I see a GCF, right? Factoring can happen. What else can happen in these problems? Adding fractions, right? Let me see if there's a problem like that. Blah, 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 blah. Here we go. Perfect. Yeah. Okay. So this problem right here, I mean, there's a little bit you can do over here. Right? You can write cotangent, cosecant in terms of cosine and sine, but you see how there's a lot more you can do over here, right? And there's two fractions. Are there any fractions on the other side? So do you see how it makes sense to combine the two fractions? Because it's supposed to be equal to something that doesn't have two fractions. Right? So I'm going to combine them. The very first thing I've got to do is remember what this is. Cosine of negative x equals? Cosine x, 11. And again, here's the picture I have in my mind to help me remember that. So I have this picture in mind. Here's an angle x. Cosine of x is positive something, right? Cosine of x. Negative x, isn't that the same triangle? And in fact, the x side is still positive. Of course, it's the same x side, right? So that's why cosine of x equals cosine of negative x. What about sine? Sine of x is this y piece. What's cosine? What's sine of negative x? Negative y. Okay, maybe. So that's the picture I have in my brain is, okay, when it's here versus here, cosine stays the same sign, but sine changes signs, because up here it's up and down there it's down. That's the picture I have in my head. I don't actually have that memorized. I just kind of see that picture in my head. Okay, so I can rewrite this as, so I'm going to start with this side. So what am I trying to do? I'm trying to work with it until it looks like the other side. Now just to remind you guys, I can work with both sides. Let's try that right now. Let's try that. So this is supposed to equal negative 2 cotangent x cosecant x. So over here, we can get LCD, right? But real quick, over here, what's like almost the only thing I can do here? Rewrite in terms of, yes, this would be negative 2. What's cotangent in terms of cosine and sine? Cosine x over sine x. And what's cosecant? 1 over sine. So I get negative 2 cosine x over sine squared x. Right? I don't know if that's going to help me. We'll see. That's like the most I can do on that side that makes any sense. Right? And what do I do over here? I need to get a... Yeah, so this guy is missing him. Right? I really want this to make sense. If this statement is supposed to be true, and one side has fractions and the other one doesn't, it makes sense to put those fractions together to make it start looking more like the other side. Not only does this side not have fractions to start with, it doesn't have two fractions. So I might as well combine them and hope that some stuff cancels. So on the top I get 1 minus cosine x, right? Minus 1 plus cosine x. All over, what do I get when I multiply 1 minus cosine x times 1 plus cosine x? I like it. Is everybody with me? I got the bottoms be the same, so I did this top minus this top.
Should you separate them?
Well, if I separate them, I go right back to where I was. I want to keep it as one fraction, right? That's the whole idea. I had two fractions. I want to put it together into one fraction. What's on the bottom? What's 1 minus cosine squared? Sine squared. And what happens here? What's 1 minus 1? 0. And what's negative cosine minus cosine? Negative cosine, right? You guys see that? Negative cosine minus cosine. Negative cosine minus cosine. How many negative cosines do I have? 2. So negative 2 cosine. Is that, are they the same? Yes. Yes. Is that better? So you could either work with either side all the way until it looks like the other side. And we did several problems like that. Or you could do a little bit to both sides and hope that they meet in the middle somewhere. So does this equal that? Yes, because this is this, is this, is this, is this, is this. So that equals that. You guys see that there's a chain there, right? So that means that the first guy equals the second guy. We verified it. We showed that it was true. We made one side look like the other side. Is that better? There comes a point where you got to understand what you're supposed to try to do, and you're just not comfortable with it. And that's why you have practice. That's why you have homework. That's why you have help to go to with specific questions that you have, right? Let's try one more out. I don't know. If you have any specific ones you want to see, let me know. Yes? This guy here? Am I in the right section? Yeah? Okay.
Maybe start that one.
Say again?
Maybe start this one.
Okay. So, does anything jump out at you at all about this problem? Related to what we've been talking about so far? There's a fraction on one side, not on the other side, right? What else? The basic identities have what's in them? Squares. I see one side is squared. That might come into play, right? Secant squared is part of an identity, correct? And you can work on both sides. So, how do I say this? All right. This idea of multiplying by the conjugate shows up so often. And just real quick, remember what conjugate means. So if I had square root of 7 over square root of 4 minus square root of 3. Square root of 6 minus square root of 5 there. Square root of 4, of course, is doable, so I don't want that. Remember this? How do I simplify this? I pretty much just told you just a minute ago. How do I simplify this? I know this isn't trig, and it doesn't matter because your final's going to have everything, so we might as well talk about this again. How do I simplify this? And what is the conjugate? Square root of?
Square root of 5 minus square root of 6.
Well, sort of, yeah, but not really.
6 plus right.
Yes, you just change that sign in the middle. That's it. And yeah, same thing, top, bottom, right? So on the top, I get square root of 42 plus square root of 35. What they do on the bottom, I get 6. The middle terms cancel, right? Minus 5. So the bottom just becomes 1. Okay, so when I have one side is a fraction, the other side isn't, sometimes what I could do is multiply by something like a conjugate, right? Let me think. I haven't really thought about this one. Let's try it. Let's just try it. Let's If it doesn't work, that's an awesome example of that's part of the process. So we're gonna work with this side. We're gonna multiply by the conjugate of the bottom. What's the conjugate of the bottom? Same idea, exactly the same idea. Cotangent minus cosine. This might not work, which is actually good, because I want you to see something that doesn't work. Let's see if this works. So let's worry about the bottom. I'm not gonna worry about the top of the money. If the bottom doesn't work, we're gonna not worry about it. So there's the top, that times that. Let's look at the bottom, because what do I want the bottom to kind of come out to be? Something singular, something nice. So we'll see what happens. So on the bottom I get cotangent squared. The middle terms cancel, right? Minus cosine squared. Now that doesn't scream anything out to me. There is some stuff I could do here, but that's not immediately looking like it's gonna be useful. Do you guys see that? Okay. So what else can we try? So just to show you what you could do, if you write this in terms of cosine and sine, it'll be cosine squared over sine squared, right? And then you can actually take a cosine squared kind of out, but that doesn't look like it's going to get anywhere too useful too soon. Let's see if there's anything else going on. I want cosine. Oh, the top looks like it might do something nice. Let's see what the top comes out to be. Let's see if you guys are cool with this. Secant theta times cotangent theta, right? I'm going to start to FOIL this. What is secant theta? 1 over cosine. And what's cotangent? Cosine over sine. So do you see how, so I'm going to write secant like this, I'm going to write secant like that, and I'm going to write cotangent like this. Do you see how the cosines cancel? All right, and then you get, what's secant times cosine? Does anyone know that one? Secant times cosine. What is secant again? So what's 1 over cosine times cosine? 1. So that'll be minus 1. What's tangent times cotangent? What's cotangent again? Even more fundamentally, 1 over tangent, yes? Isn't cotangent 1 over tangent? So what's tangent times 1 over tangent? Positive 1. That's nice, see that? And then tangent times cosine, here, we'll worry about that in a minute. Well, what is tangent? Sine over cosine. Those cancel. So some stuff happens, and again, how do I say this? What students don't get, so we're doing this problem right now. Did you hear what I said earlier about I don't know if this is the right way to go? Did you guys hear that? Yes, I don't care how good at math you are. When you're given a trig identity to verify that you haven't looked at or you don't remember or whatever, you're gonna try some stuff out. And it might not work, which is beautiful. It's part of the process. So on the top, so here on the bottom I get cotangent squared minus cosine squared. Okay. So some good stuff happens on the top, but it looks like it's not gonna get anywhere too good too soon. Right? I mean, the minus 1 plus 1 cancels, right? And what's 1 over sine? Cosecant. So I got cosecant. What do you guys work well? No. Minus 1 plus 1 cancels. Minus sine over cotangent squared minus cosine squared. All right. It's not looking too promising. some stuff happened, but it looks like, I could probably keep going, but there might be a better way to do this. So this was just one idea that was thought of. So let's go back to the beginning. Maybe. We could keep trying to do stuff with this, because again, like I said, the bottom would be cosine squared over sine squared minus cosine squared. I could take a cosine squared out. Try to see if that does some stuff for me. Right? Maybe? Okay. So, we can either try to keep going, or we can go back to the beginning. What's something else I could try to do on this problem?
Rewrite it,
Rewrite it in terms of
sine cosine.
sine and cosine, right? So that's something else to try. So I'm going to leave this up here. Let's see, 42. So let's see, let's rewrite everything in terms of sine and cosine. So secant is 1 over cosine. Tangent sine over cosine. Cotangent is cosine over sine. Cosine is cosine. Okay. And we're trying to get to secant squared. What's secant squared, by the way? Let's look at the other side. What is secant squared? What identity does that come from? Secant? Yes, 1 plus tangent squared. And isn't tangent sine squared over cosine squared? That's what tangent squared is. Are you guys with me? So you see what I did was I tried something out on one side, it kind of didn't get anywhere. I'm going to try something else out, but now I'm going to start on the other side also to see if I can see where they meet. Can I add these together? For example. I could, but then it would go right back to here. I don't know if you guys see that. So that doesn't seem to go much further than that. Okay. So let's see. Over here, what can I try to do? What kind of sucks here is all the multiple fractions I have. Does anybody agree with me? So let's try this. Do you guys see why it would be good to multiply by cosine? Top and bottom? Yeah, because I cancel both of those. So the top just becomes this. Now what does the bottom become? Cosine squared theta over sine theta plus cosine squared theta, right? Now how do I get rid of this fraction here?
Sine.
Multiply by sine, top and bottom, right? You guys see what I'm doing? All right, so I multiply this by sine, multiply this by sine. We get sine theta plus sine squared theta over cosine squared theta plus sine theta cosine squared theta. Okay. So let's see, on the bottom, I can actually take out a cosine squared, right? You guys see that? And actually, this is even better. I want you to notice something. Do you see how I had this and then I distributed this sign? But you see if I leave it like this, the top, you guys see that? I just multiply the sign and got here, right? But if I leave this on the top, what's going to happen? These cancel out.
So you're,
Whoops. Let's see if I did everything. Yes, yes, and then sine theta, sine squared, sine, okay. Cosine squared, sine theta, okay. Bless you.
Thank you.
And
let's see,
The one plus sign cancel each other out, does it make one?
where we at? Sorry.
At the end, where you cancel.
Yeah.
Plus sign, they cancel each other out, they don't make.
Yeah, 1 plus sign divided by 1 plus sign is 1, right? Okay. That's a squared, okay. So, let's see, how do I make this look like that? Let's see, so this will be, this is sine theta over cosine theta times 1 over cosine theta. It's tangent times secant. Let's see. Cosine plus sine, cosine over sine plus cosine. I like it. Multiply by cosine to get rid of that stuff. Cosine multiplied by cosine. Okay, I like it. And then sine theta. So here, okay, I like it. Multiply by sine. Let's get here. Cosine squared out. Sine back out. Those cancel. That becomes that. Let me see. Tangent theta times secant theta. It's not secant squared. I wonder if that's a typo.
Because questions that,
Oh,
that might be
thank
true or
God.
false.
Okay, if it's false, find an appropriate fill. Okay. So most of these problems, when they give it to you, it's a known identity. Okay, let me make sure you guys understand. Is everybody semi-cool with what happened here? Again, it was a problem where I wasn't really sure what to do, so we decided to go ahead and rewrite everything in terms of sine and cosines. When you have fractions inside of fractions, a really good natural thing to do is to just clear the inside fraction. So we multiply by the bottom here, we multiply by the bottom here, so that we don't have any fractions inside of our fractions. That's a natural thing to do. And then I notice that parts will cancel with each other. And then I get here, sine theta over cosine squared. So that's sine theta over cosine theta times 1 over cosine theta, right? The bottom has 2 cosines. What's sine over cosine? Tangent. And what's 1 over cosine? Secant. Is that equal to this? No. So that's false. This identity is false. So what should be here is this. Okay. That makes me feel better. I was like, wait a minute, this isn't true. Okay. So this is a problem. Most of these are going to be the one they give you is true. These set here, some of them could be false, which is a little evil. I will agree. But again, what's more important? Okay. Every time we do any example problem, anytime, anywhere from any section, the most important thing is, why did I try what I did? Why did I do what I did? Because that's what you're going to have to do. And did I choose the good thing to try first? Did I pick something good to try first? Our first attempt, was it successful? Did we get somewhere good on the first thing I tried? No, we didn't. That's part of the process. I didn't care, because that just told me, okay, that's not a good way to go. Let me try something else. Okay. So what are some major things? When I have 2 fractions on one side and no fraction on the other, I try to combine those fractions, right? If I see something I can factor, I try to factor it. If I see a squared trig, I look at my Pythagorean identities, try to use those. Okay. Is there a blanket statement I can make to do every identity? No, there isn't. But there are certain things you can look for. You look for fractions, and you look for combining them. You look for identities, for sure, and try to replace them. You look for fractions inside of fractions and try to clear them. Right? Just multiply by their denominators. Okay. So which approach will work when? I don't know. I don't. That's part of this whole thing, is just being comfortable with trying different things out. Okay. So do you understand that? That is part of this process.
right? That's just part of the process, is trying something, and if it doesn't quite get you there, you go back and you try something else. That's part of the process. It doesn't mean you don't know what you're doing. It doesn't mean I didn't tell you something. It means that's part of how these things work, is getting comfortable with playing with these identities. Okay. Maybe, let's see. Let's do this. Let's do one where they aren't false. Oh, this is why it's a bonus. Okay, I love it. Let's see what's an interesting looking one. I don't like this. Yeah, these are just simplifies, nothing too crazy. Yeah, this section, there's not a lot of identities you can use. 9.2 is where we learn like the sum and difference and double angle, all those kind of things. Let's see. Oh, here's 9.3 is actually double angle. This is sum and difference. I don't think they have a lot of, they don't have any identity verification in this section here. Okay, here we go. This is in the extensions. Oh, that's this problem here. That's right. We looked at that problem earlier. Okay. And for example, I mean, look right here at number 50. Number 50. Oops, let me zoom in a little bit. See again? I'm sorry? Number 50? I'm sorry. Oh, if we did, I don't remember. I don't remember doing this problem. Number 50?
Like cosine x, cosine y plus cosine y cosine x, did I do that?
I'm sorry. So which side are you doing
On the
something
left
to?
side.
This side?
Yeah.
And what are you doing to it? Are you trying to distribute the cosine?
Yeah.
Okay.
My bad.
Alright. If I have log base 7 of 4 plus 3, for example,
Oh, okay.
can I distribute the log? No, I have to do the inside first, right? If I have the square root of 16 plus 9, that is not 4 plus 3. I don't distribute the square root. Okay. Do I have an identity for cosine of the sum of two angles? Yes, in fact, it's one you have to memorize. Do I have an identity for the cosine of the difference of two angles? Yes. So in this problem, do you see how this side, can anyone tell me what this side would be if that was an x instead of a y? If it was cosine squared x minus sine squared x. Sorry? What's cosine squared of angle minus sine squared of angle? Okay. It's cosine of 2 angle, right? So it'd be cosine of 2x in this case. So it's the double angle formula for cosine, right? Which is one you have to memorize. So like, for example, does anyone know what sine of 2 theta is? Sine of 2 theta. 2 sine theta cosine theta. That's the nice one. Sine is the nice guy. Cosine's the asshole. Because if I say cosine 2 theta, there's 3 options. One of them is cosine squared theta minus sine squared theta. But do you notice, of course, these angles aren't the same. So there is 0 I can do on this side. I could actually factor it, but I mean, it might. But do you see what I'm saying? There's nothing I can do. There's a ton of shit I can do on this side. Bless you. Do you guys see what I'm saying? So you replace this with what it is. What is cosine of x plus y? Remember, cosine is an asshole. Me. You got a plus. That's nice. I'm going to put a minus. And then sine finally gets a turn. And then the only difference with this guy is plus. Do you guys notice something really nice here? Isn't this like a difference of squares kind of multiplication? Do you see how the middle terms are going to cancel? Okay, that's all I'm going to do. I don't know if we did. Is that a homework problem? Probably not. I don't think so. So let's finish this out. So what do I get? What's cosine x, y, cosine x, cosine y times cosine x, cosine y?
Cosine x squared, cosine y squared.
Yes, cosine squared x, cosine squared y. The middle terms cancel. Does everybody see that? One is minus something, the other is plus the same thing, right? Beautiful. So then I get minus sine squared x, sine squared y. Now somehow I have to get it to be cosine x, cosine squared x minus sine squared y. Do you see, there's cosine squared x, and there's sine squared y, but how do I kind of get rid of these two things, right? So let me see, how can I tell you this without just doing it? Well, all right, let's see, let's try something. Let me pull this up here. Do you see how there's obviously a bunch of squares running around, right? Do you guys see that? Bunch of square stuff running around. And I want, all right. What do I not want? What do I wish I could just erase? And then I would be done. And there's two things that I wish I could just erase.
Cos squared y, sine squared x.
Yeah, cos squared y and sine squared x. If I could just erase those, I'd be done, right? So instead of erasing them, let's try replacing them. And to be honest, right now I don't even know this is going to work, but this is just the next thing I thought of. I really want to let you in on that. Nobody, I don't care how good at math you are, you don't immediately know how to do any problem you're given. You just don't. But I know what to try, right? I know a lot of things to try. That's what knowing math is knowing what to try. So let's do this. What is cosine squared y?
1 minus sine squared.
Good. And what's sine squared x? Because that's the one I don't want, right?
1 minus cosine.
Let's see if this is going to go somewhere good. I think so, yes. So again, there's no blanket statement I could ever make. But you see what I'm going to try something. Those are the two things I wish wasn't there, but I can't erase them, but I can replace them. Let's see if this does anything for me. What do I get here? I get cosine squared x minus cosine squared x sine squared y, right? Minus, all right, let me make sure everybody's cool with this. Minus sine squared, right? Plus, is everybody cool? Plus sine squared, cosine squared x sine squared y. Does anything cancel? And what are you left with? Done, right? Now that one is a decent one. And again, why was that one? There was a step there that wouldn't come automatically to you, correct? I don't think all of us would think to do this. Some people actually have given this problem too, and they just sort of erase that. They're like, there, Jeff, they cancel. How? What do you mean? How do they cancel? But again, this is under the extensions, which basically always means kind of like bonus. But it's still good to see what you can try. So that's what math really is. It's just increasing the number of things you know to do so you can have more things to try given a problem. Math is not, I gotta get to a point where I know exactly what to do with every problem I'm given. That is impossible. I don't care who the hell you are. Maybe. All right. I like it. So do you see, okay, I'm sorry guys. I don't mean to sound like I'm upset, but this is what I live on. Questions. I don't know if you guys have noticed. Do I ever ask you if you have any questions? I do. And this is what I mean by it. You can have a very specific question and say exactly how do you do step 3 on number 27, part B. Or you can say, how the shit does proving identities work, right? Maybe don't say it like that, but, and then I'll answer. It's crazy. It's crazy. Okay. So hopefully that helped a little bit. it's all about knowing what to try and understanding that if you try something, it's not gonna definitely work. It just isn't. So you can imagine, I can't give you a ton of these on a test, because if you try like 5 wrong things, you're wasting a lot of time, right? So I try to give you some that are really obvious. What if I give you something that's got 2 fractions on one side, you should immediately know, like denominators, get those together, right? I'm gonna give you stuff that's kind of blatant at you. Okay, maybe. Okay. So that was good. I like it. Okay. Anything else? Any other specific questions or general questions or anything? Okay. No. Okay. So let's do this. Let's remember before we get into the next chapter. I want to do like a couple more, maybe one more trig equation solving. That's the last thing we did. So let's do a semi-basic one here. Let me see. Yeah, I think that'll be what I want. Yes. I think, yeah, sure. Yeah. Okay. So let's say I have to solve this equation. So the funny thing about solving equations is it basically stays the same always. They're just slight considerations based on what's in them. But does anything jump out at you as to what to do here? Say again? I'm sorry? What about it? I'm sorry? So here's a general thing about solving trig equations. In general, you don't want multiple trig functions kind of running around. It's nice that this is all sine, right? So I don't want to replace sine squared with 1 minus cosine squared, for example, because then I'd have sine and cosine that don't really play together well. I like that they're all sine. How do you solve this equation? Okay, so what comes out? Sine theta. What are you left with? 1 minus 2 sine theta. So then what do you do from there? So over here, if I factor an x out, what's the next thing I would do? What's the next thing I would do?
Eliminate the x here with parentheses on your own.
Say again?
Eliminate the x here with parentheses on your own.
No, I can't eliminate the x. Real quick, why can I not divide by x? Because what could x be? X could be 0. So you can basically, unless you're really careful about it, you can never divide by a variable expression. You can't take something and divide by a variable because that could be 0 somewhere. Well, come on guys, what do you do? Yeah, either this is 0 or this is 0, right? Is that cool? Right, that's the basic idea, and then you solve for x, no big deal. So what do I do here? Either this is 0, right? If sine theta is 0, isn't this whole thing 0?
Yes.
Kind of like what I call a trivial solution. Or, what if this expression is 0? Is the whole damn thing 0? And of course, that's why this number has to be 0 for that to work. Because that's the only one that requires one of the two numbers to be something, specifically 0. You with me? If this was 8, then this could be 8 and 1, 2 and 4, 16 and 1/2, 800 and 1 over 100. There's an infinite number that's got to be 0. Okay. So when is sine theta equal to 0? Now where? Sure, yes. And the first place at 0 is at 0. And another place at 0 is at pi. So it's 0 here. Yeah, degrees. 0 there and it's 0 there, right? Did I give us any interval to live in? So you better give me every answer. So, are these equally spaced from each other? Aren't they pi apart both ways? So I can say the answer is 0 plus or minus pi. Okay, so the answer is actually just plus or minus pi k. When you tell me, like, when is sine 0, at any time it's on the x-axis. Well, when is it on the x-axis? Any angle that makes you end up here, and any angle, so isn't this 7 pi? Isn't this 80 pi? I mean, so any multiple of pi will make sine 0. Is that cool? That's all that says. And am I done?
No.
No, of course, because I got this other thing. So how do I solve this?
Subtract one from both sides.
Say again, sorry? Yeah, subtract 1. And then divide by -2. Is that cool? Get out of there, 2. So subtract 1, divide by -2. 1 is sine 1/2. Yeah, so pi over 6, or at, what else is sine 1/2? 5 pi over 6. Are those equally spaced apart? You sure about that?
We know my bad.
Nope. So you need 2 separate lines then, right? So now, if I start here, how do I get to the next answer? I have to go a full rotation around, correct? Okay, so this will be plus or minus 2 pi k, and this will also be plus or minus 2 pi k. Why did I only need 1 line here? Because I can get from one answer to the next answer and back using the same multiple. They were equally spaced. Here I need 2 separate lines because I can't get from this to this and then back to this using the same addition. Really, you see that? Okay. So that would be the answer, because I didn't give us an interval in which it should live. Right? What would the answer be if I would have said the answer has to be in 0 to 2 pi? What would the answers be? 0?
5 over 6.
Well, let's see, for this one, it would be 0, pi, 2 pi, right? So from this one, it would be 0, pi, 2 pi. And from this one, yeah, it would be pi over 6, 5 pi over 6. And that's it. So if they give you an interval in which you can do your answers, you don't have to do this plus or minus pi k stuff, right? Because you're not allowed to rotate forever if they just say you can only go from 0 to 2 pi. You're not allowed to rotate forever, so you don't need this. But if they don't give you an interval, then you need this, because then you're allowed to rotate forever. Okay, maybe. Okay, what about, let's see, let's do one more, I think. Yeah, let's take one out of the book. Let's see what the book runs out. This was 9 5, I think. Where am I? Jet, push it. All right, here we go. Let's see, these are really basic ones. All right, let's do this. All right, I love it. Bless you. I mean, not bless you. Sorry, you're fine. Okay, let's do this. Yeah, number 19. I don't think they asked you your opinion on it. What's a good first step here? What do I try to get by itself? Yeah, divide by 2. I'm trying to get cosine by itself, because then I know what the angle has to be to make it equal the value. So if I divide by 2, I know that this says cosine of something is negative rad 2 over 2. And it says to give it between 0 and 2 pi. I kind of like they don't include 2 pi, that's good. Now, do not worry about the 3 yet. I like it. So this says cosine of this angle is that. What angle makes cosine negative rad 2 over 2? Where would we be? Which quadrants to make cosine negative?
2.
2. And no, 3. That's where the x is negative, right? Cosine goes like x. So Cotillo don't help you with that. So I know I'm in quadrant 2 and 3. What's the reference angle that would make cosine rad 2 over 2?
45 degrees.
45 degrees, or otherwise known as pi over 4. So I know the reference angle has to be pi over 4. So what are the two angles? This is pi over 4 less than pi. 3 pi over 4. And the other one is pi over 4 more than pi. 5 pi over 4. Is everybody right? Pi over 4 before pi is 3 pi over 4. Pi over 4 more than pi is 5 pi over 4. Now what I do you notice how it says 0 to 2 pi?
Yeah.
Well, this is what I do. Let me see if you guys, all right. I'm going to do this. This makes this easier. Whenever you have a multiply here, I'll show you. I'll show you why this makes this easier. Because am I done solving this yet? Because what do I have to do? I need to know what theta is. So what do I do to figure out what theta is? Divide by 3. So I get, you're not working too good. I get theta equals, is this cool? 3's cancel? Pi over 4 plus 2/3 pi k. And here I get theta equals 5 pi over 12 plus 2/3 pi k. Yes?
So you took plus, the 2 pi k because you gave yourself like a limit.
I'm sorry?
So you know how it's like plus and minus in the other one?
Oh, yeah, okay, I'm glad you said. I'm not doing minus because I have to live within 0 to 2 pi, right? So if I go backwards, I start getting negative angles. So, but I mean, yeah, you can put those there, but it's not gonna really help us. Okay, so again, all my answers have to be between 0 and 2 pi, correct? Right. Okay, so theta could be, let's take this first step. Pi over 4. Now add one of these, right? Like k, if k is 0, don't I get pi over 4? If k is 1, I get pi over 4 plus 2/3 pi, right? So let's see, pi over 4 plus 2/3 pi. I can add those together, right? So I get 3 pi over 12 plus 8 pi over 12, 11 pi over 12. Where's that answer at? What quadrant? 11 pi over 12. It's almost but not quite how much? It's just shy of how much? It's just shy of a full pi, right? So what quadrant is that in? Second quadrant. So I'm still good, right? Because I'm supposed to be the first 4 quadrants in the first rotation. Okay. So go to the next one. Let k equal 2. It'll be pi over 4 plus 4 pi over 3. So now I'm going to get 3 pi over 12 plus 16 pi over 12. It's 19 pi over 12. Is that still good? Have I gone past 2 pi yet?
No.
To be past 2 pi, it'd have to be above 24 pi over 12, right? So I'm still within what they told me to be within. So if I try to do 3, won't that be pi over 4 plus 2 pi?
Yeah.
Won't that be too far? That'll be more than 2 pi. I'm supposed to stop. Okay, so I know those are the 3 from that one. Now I do the exact same thing with this one. Right, so for this one I would say it's 5 pi over 12. Then I have to add 2/3, which is, let's make this right now, let's make this 8/12. It's going to make it a lot easier. So if I add 1 8/12, I'll get 13/12. That is still good. That is just past pi. That's in the third quadrant. I'm still good. If I add one more 8/12 pi, that'll be 21
Yeah.
12ths. Do you see I'm still good? I haven't gotten to 24 12ths yet. That would be past 2 pi. If I try to do it one more time, I obviously go past 24 pi over 12. That's 2 pi, right? So I can stop right there. It gets really weird when they have a multiple on the angle. So this is my suggestion. If they give you something you have to live within, this is my suggestion on what to do to make sure you don't include too many. And make sure you get them all, and make sure you don't include too many. Okay. Maybe. So solving trig equations will come down to what angle makes this that at some point. That's what you're trying to get it to. You're trying to get it to a point where you have a trig equals number. Because then you can just think, what angle makes that work? That's part of the answer. But it's because it repeats so much. That's why I get more answers. Right? Cosine is negative right 2 over 2 in multiple places. That's why I get multiple answers. Maybe. Okay. So. Let's do a little bit of new stuff today. Okay. So I teased this a little bit last time. So this is going to be an extension to Pythagorean theorem and an extension for trig to deal with triangles that aren't right triangles. So they're built on right triangles. But like I said last time, so let me set something up. Let's see. Okay, so there's a general non-right triangle, right? So the first thing we're going to do is we're going to develop what's known as the law of sines. So it's going to be some relationship that only involves sines. Right, kind of makes sense. What's the easiest way to make a couple of right triangles out of this triangle? Yeah, I like it. Somebody just went like that. So if I draw this in, let's call it y. Kind of makes sense. Can somebody tell me, let's see, can somebody tell me what sine of A is? No. Which right triangle does A live in? Do you guys see what I mean? Which right triangle has angle A? Does this triangle have angle A? No, this one does, right? So let's try this again. What is sine of A? Y over C. Is everybody with me? Okay. And what's sine of C? Now, which triangle are we looking at? I'm sorry, blue is down. What's sine of C? Same way. Y over A. Do those two share anything? Why? I love it. Now watch this. Watch. Is everybody cool with what just happened? We started with a triangle that wasn't right. We don't give a shit because we can make a right triangle. We can make a right triangle, right? This is just the definition of sine for that angle, and this is just the definition of sine for that angle. Yes? So all those are. Can I solve them both for y? Well, let me solve one of them for y. What do I hear by solve for y? Yeah, c sine A. So let me put that into the other guy. I'm going to use this in here. So I get sine C equals C sine A over A. And again, when we do a lot of steps with trig stuff, you start to lose the thread. All trig is ratios of sides of right triangles. And that's basically very much in your face what we did here. But then we can start doing stuff to it. Right, so watch this. If I divide by C, do you see how this becomes a very nice analogous thing? Yes? And I don't know, let's see if you can do this without, let me save some time here. Do you see how I made side B on this, on the bottom? Right? Couldn't I have made side A on the bottom? Couldn't I have then drawn this in to make a right, let's see if I drew it to make a right angle here? You guys see what I'm saying? If I would have turned it around, wouldn't we have drawn it in like this? Yes? Couldn't I do the same thing then with B and C? So what ends up happening is this. That is too beautiful to believe. That is too nice to believe that this exists. For any triangle, I don't care if it's a right triangle or what it is, this relationship is true. And you're all like, okay, John. So, what does that mean? What that means is,
Is that like an order or is that just a list?
I'm sorry, say again?
Is that like an order or is that just a list?
It's just a equivalency.
Okay.
There's no order to it. So whatever this is equal to this, is equal to that. Okay. Let's take a triangle that we know and show you that this works. Let me see if I can do this semi-quickly. Yeah, okay, so a 30, 60, 90 triangle, right? So let's say this is A, this is B, and this of course is C. So again, this works for every triangle. So I just want to start with something concrete. So what this says is sine of A over A equals sine of B over B equals sine of C over C. So let's see where this works. What's sine of A? Yes. What's sine of 30 degrees? And actually, let me do, sorry, let's make this more, sorry guys. Well, actually, yeah, leave a little A there, B here, C here. Let me make this a little more specific. If I make this 1, this is going to have to be 1/2, and this is going to have to be rad 3 over 2, because it's across from the building thing. So this is that 30, 60, 90 triangle that we did before. So sine of A, what's sine of 30 degrees? What's sine of 30 degrees? 1/2. So it says 1/2 to 1/2, that's 1. So that's what that is. This is supposed to equal sine of B over B. What is sine of 60? Rad 3 over 2. Still 1. So those are true, right? 1 equals 1. And what's angle C? That's going to be the right triangle, the right angle, right? So what's sine of 90? Sine of 90 degrees? 1. And whatever 1 is? 1. Okay, so that's a silly example. So for any right triangle, it's obviously going to be true. So let me show you the full power of this. If I have something that's not a right triangle, before today we would say trig doesn't work. Well, now we know better. So let me see. So here's just some general triangle. Let's see. Let's make this 10. I'll make this 70. Make this 50. And that makes this 60. Okay, I like it. So then I'm kind of inherently, this is going to be, do you see how angle B is across from side B? Makes sense. So this will be angle A, and this will be angle C, and this will be side C. Okay, so which angle and side make a complete ratio? So remember, this is called the law of sines. Sine A over A equals sine B over B equals sine C over C. Which angle and side are completely known in this triangle? Yeah, I know C. I know everything about C, right? That means law of sines will work. In order for this to work, I have to know one of these completely. And then I have to have another one where I don't know one of the two things, right? So let's just take this, so we know all about C, so let's talk about this here. So sine of C over C, so this will be sine of 70 over 10, right? Is that cool? Sine of angle C divided by side C equals sine of B. What's B? Angle B. 60 over side B. So can't I solve that for side B? I like it. So to solve this for side B, I can multiply the B up. I can divide the sine 70 down. And I can multiply the 10 up. And if you have to do that in multiple steps, that's fine, right? You can think of it as cross multiplying, then going from there. Cross multiply, bam, bam, and then divide by sine 70. So let's see, somebody help me out. Throw the old calculator, what do you get? Make sure you're in degrees, right? For this problem. I think my calculator's dead. Kind of sucks. It's almost dead at least. Oh, it's not so bad.
So we use the law of sines to find out one side, which means like,
You can use the law of sines to fully solve a triangle. You can figure out all the sides and all the angles. When does law of sines work? If I know it, at least one angle and the side across from it. Then law of sines will work.
that's where you make like sine A equals sine B, to find out what side B is.
No. So in order to solve an equation, I need to have only one thing I don't know. So in this case, we don't know B. So that means I have to know everything else, right? So in order for law of sines to work, I have to have a complete ratio. I have to know at least one angle and how long the side is across from it. Then I can make a complete ratio. Then I know law of sines is going to work. So what do you guys get for this? Yeah, 9.216? Yeah. I like it. So then, how would I get, can I use Pythagorean theorem to get A?
Maybe.
No, do better than that. When can I use Pythagorean theorem? What kind of triangle does it work on? What kind of triangle does Pythagorean theorem work on? A right triangle. Do I have a right triangle?
No.
So can I use Pythagorean theorem? No. What do I do then? Sine of 70, sine of C divided by C equals sine of A, right? Divided by A. I can just I did the one for B, let's do the one for A. It works the same way. So then A is going to be 10 times sine 50 divided by sine 70. And then use the old calculator. Scheisse. Oh, now you're almost dead. Okay. Was it 50? Yeah. So what do you guys get? 8.152. Real quick, why does it make sense that angle C is across from the biggest side? Why does it make sense? Yeah, because the angle's bigger, so it opens wider, right? So if you want to see how big of a geek I am, I always think about Star Wars, where he put the stick in the thing's mouth. You guys remember? Whatever the hell it's called. Put it in the mouth. So the bigger the mouth, the bigger the stick you need, right? So this has got a big ass mouth and needs a bigger stick. This has got a much smaller mouth, smaller stick. What's the smallest side? This one, across from the smallest angle. It's beautiful. You can kind of check. your work as you go, right? Okay. So this is a good little first step. This is awesome. We got tomorrow to finish up law of sines. We'll talk about law of cosines. Definitely come with questions. Like I always want questions. And tomorrow I'll have the practice test, and of course Thursday will be review day, right? For the test. Okay. And if you weren't here earlier, real quick, up in Canvas I put the current timeline. We'll see, it depends on how far we make it tomorrow as to what the test is gonna cover. I think it's probably just gonna go up through 10.2, but we'll see. All right. So I'll see you tomorrow. Unless you have questions, come see me here or in my office.